Okay, so now we're going to talk about the alternating series test. And so let me explain to you what an alternating series is. An alternating series is just a series that alternates sign. So here we have 1 minus a half plus a third minus a fourth plus a fifth and so forth. Well, the nth term of this series would be minus 1 to the n plus 1 over n. Now you can plug in values. If you plug n equal 1 in here for this, you'll get the first term. If you plug n equal 2 here, you'll get the second term. N equal 3 give you the third term, and so forth. And that's actually the alternating harmonic series, and that series converges. Now the next one is negative 2 plus 1 minus a half plus a fourth minus an eighth, and so on. And its nth term would be negative 1 to the n times 4 divided by 2 to the nth power. Well, this series is a geometric series with r equal negative a half, and since the absolute value of r is less than 1, this series converges from what we learned about geometric series. This next series, 1 minus 2 plus 3 minus 4 plus 5, where the nth term is negative 1 to the n plus 1 times n, this series is actually diverges by the nth term test because the nth term does not approach 0, so therefore this series must diverge. Now we can use this next test to prove convergence of certain alternating series. So this test says that if a sub k is greater than or equal to a sub k plus 1, and then of course all the terms are positive for every k, and that the limit of the nth term as n goes to infinity is 0, then the alternating series given by this is convergent. Now remember, when I give you a sigma here and I don't put anything below it or above it, it's understood to go from 1 to infinity. Okay, so let's determine if this series here converges or diverges. Okay, so what we have to show is we have to show that each term to the right of the successive term is less than or equal to the term before it. So basically, we're kind of trying to show that the series is a decreasing series. So what I want to do here is I'm going to get a function that corresponds to that series. So the series is 2n over 4n squared minus 3, and the corresponding function would be 2x over 4x squared minus 3. And I'm going to see if this function is decreasing, because if this function is decreasing, then this part up here would be satisfied. So if I take the derivative of that, and you can do the derivative, just use the quotient rule to find the derivative, notice that the denominator of the derivative is positive and the numerator is always going to be negative. So therefore, since the derivative is negative, then this function must be a decreasing function, and if this function is a decreasing function, then this series is a decreasing series. So we've shown the first part of that. Now the second part of this, we have to show that the limit of the nth term is 0 as n goes to infinity. And that part's easy, because if you take the limit of 2n over 4n squared minus 3, since the degree of the numerator is less than the degree of the denominator, we know that goes to 0. So therefore, both of these are satisfied, so we know that this alternating series that we started with must be a convergent series. Okay, now the next one, I have 2n over 4n minus 3 instead of 4n squared minus 3. Now you can show that this, if you take the corresponding function that corresponds to this, 2x over 4x minus 3, you can show that it's a decreasing function the same way as I showed it in the previous example. So I'll leave you to do that. But however, if I evaluate the limit of the nth term, I actually get 2 over 4, which is a half, and it doesn't equal 0. So therefore, the alternating series test will not apply. But if you go back and check your nth term test for divergence that we talked about earlier, you'll actually find out that this alternating series will diverge. So again, just go check the nth term test for that. Okay, now the next theorem says that if I have an alternating series, if this is an alternating series such that the terms are decreasing and positive for every positive integer k, and if the limit of that nth term is 0 as n goes to infinity, then the error involved in approximating the sum of the series by using nth partial sums, for instance by using the nth partial sum s of n, is less than a sub n plus 1. So it's less than the error is less than the n plus 1th term. So an example there would be prove this series 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial, etc., where the nth term is negative 1 to the n minus 1 times 1 over 2 times n minus 1 factorial. We want to show it's convergent and also approximate its sum to 5 decimal places. Okay, well, it's pretty obvious that this limit would equal 0 because the denominator increases to infinity without bound, so 1 over infinity will go to 0. And you can see up here that 1 over 3 factorial would be less than 1, 1 over 5 factorial would be less than 1 over 3 factorial, and so forth. So the k plus 1th term is going to be less than the kth term for all positive values k. And so therefore, that's all I needed to show that the series converges, because I used the two things I had to show from the alternating series test. Now, in order to approximate the sum to 5 decimal places, I had to check like the second term, the third term, the fourth term, the fifth term, and so forth, until I got to one where I had all zeros out to 5 decimals, because this approximates the error. So when I got to the fifth term, 1 over 9 factorial, that had zeros to 5 decimals. So therefore, based on what this theorem says, since this is the ace of n plus 1, then my nth partial sum would be the fourth partial sum. So that would mean that if I get the first 4 terms and add those up, which is 0.841468, then that would approximate the sum of this series up here within 5 decimal places. Okay, now later we can actually show that the series converges to the sine of 1 radian, which is approximately 0.84147. Okay, now the next thing I want to talk about is absolute convergence. And if I'm going a little too fast, just freeze the video if you need to. Okay, so an infinite series is said to be absolutely convergent if the series of the absolute values of the terms is convergent. So, in other words, this series here, in order for this series to be absolute convergent, in other words, absolutely convergent, I would have to show that the series that involves only the positive terms, the absolute value of the terms, converges. So let's look at the series that involves only the absolute value of these terms. So that would be 1 plus 1 over 2 squared plus 1 over 3 squared, so forth, where the nth term would be 1 over n squared. Well, 1 over n squared is actually a convergent p-series. So since this series here, which is the sum of the absolute value of the terms, converges, then we can say that this alternating series is absolutely convergent. Now that doesn't mean it converges, that just gives it the title absolutely convergent. Now, but there's another theorem here that says if an infinite series is absolutely convergent, then the series itself must converge. So here's an example here of a series from the sine function. So the series is sine of 1 plus sine of 2 over 2 squared plus sine of 3 over 3 squared, so forth, where the nth term is just sine of n over n squared. Now, if I can show that the series that involves the sum of the absolute value of these terms is convergent, then then that would actually prove that this series itself is convergent. Okay, so the series of the absolute value of the terms would be the series of the absolute value of sine n over n squared. And since n squared is a positive number, I can write that as the absolute value of sine n over just n squared. And it's pretty easy to show that the absolute value of sine n would be less than, over n squared would be less than or equal to 1 over n squared, because you know the absolute value of sine has to be less than or equal to 1. So since this is true, then the series of the absolute values, since that's true, and we know that the series of these absolute value terms is dominated by that convergent p-series. So in other words, since these terms are less than or equal to these terms, then we know that this series here is dominated by the convergent p-series, and so therefore this series of absolute value terms must be convergent. Thus, the series that we started with, this one up here, is absolutely convergent, and therefore, since it's absolutely convergent, it must converge. Now the next thing I want to talk about is conditional convergent. If an infinite series is conditionally convergent if the series is convergent, but the absolute value series is divergent. So here's an example of one that's conditionally convergent, and I'll show you why. Okay, so we can actually show that this series converges by the alternating series test. So we can show that, and you can do that on your own. But if you took the series of the absolute value of the terms, then the absolute value of -1 to a power would just be 1. So you would simply get the series 1 over n. And we know the series 1 over n is the divergent harmonic series. So hence, by this definition, since the given series converges, but the series of the absolute value terms diverges, then this series that I started with up here is only conditionally convergent. Now there is a ratio test for absolute convergence. Let the series a sub n be a series of non-zero terms, and suppose we have the limit of the absolute value of the ratio of a sub n plus 1 over a sub n as n goes to infinity, and that equals L. Okay, if the L is less than 1, the series is absolutely convergent. If L is greater than 1 or equal to infinity, then the series diverges, and if L equals 1, we have to apply a different test because the series may be absolutely convergent, conditionally convergent, or divergent. Okay, so here's an example. The series -1 to the n squared plus 4 over 2 to the n. So using the ratio test, I would take the limit of a sub n plus 1 over a sub n as n goes to infinity. So if you replace this term, just the positive portion, because we're taking the absolute value, so the -1 won't apply. So just this portion, replace n with n plus 1, and what you'll get is n plus 1 quantity squared plus 4 over 2 to the n plus 1. Well, then you divide by the nth term, which would be this, but since you're dividing, I'm going to flip and multiply, and so I would multiply by 2 to the n over n squared plus 4. Then divide this into this, and I would get 2, and then I'm going to factor the 1/2 outside. And then if I simplify the numerator, I get n squared plus 2n plus 5 over n squared plus 4. And the limit of this is just going to be 1. So I have a half times 1. And so since the limit is less than 1, it says up here, if the limit is less than 1, the series is absolutely convergent. So therefore, the series is absolutely convergent. Okay, I've only got about 30 seconds here. So here's some practice problems. And so I've given you 3 series here, and I've given you the results, so you can use those tests that we've talked about to solve them. And then down here is a summary of all of the series tests that we've talked about so far. So if you need to, just freeze the video and study those, and I'll just leave it open until the video stops.